So the next speaker is Sooyeon Ji, a Ph.D. candidate from Seoul National University in Seoul, South Korea. And I hope you're still awake as well. Thank you so much for joining us today.
Okay, so yeah, I am still awake and I will start the presentation, and thank you for your nice introduction. Okay, so this is my presentation on our work on a pipeline to reconstruct multiple resolution QSM data using an existing QSM network, which was trained on a single resolution data. Okay, so QSM reconstruction or dipole inversion problem is a well-known ill-posed problem, which usually results in streaking artifacts in the reconstructed QSM maps. And in recent years, deep learning-based QSM reconstruction methods have been developed to overcome the ill-posedness of QSM reconstruction. And in most cases, the networks are trained at a single resolution. For example, 1 millimeter isotropic resolution for the QSMnet Plus that was developed in our lab. And these methods provide high quality QSM when the input data has the same resolution to that of the training data. However, when data with different resolution than that of the training data is used, the deep learning-based QSM tend to fail. So while the easy solution to this is to interpolate the data to the training resolution, this would result in losing some of the high-frequency information in the original data. And this is a huge problem of deep learning-based QSM because it is just not feasible to train different network for every different resolution. And although several deep learning-based algorithms were investigated to overcome this pitfall, generalization to different resolution data is still a challenging problem. So in this work, we propose to solve this problem by developing a pipeline to reconstruct the multiple resolution data using a network already trained using a single resolution. So this is the overview of the proposed pipeline that reconstructs QSM data at multiple different resolution using a network trained at a single resolution. The pipeline consists of 4 steps, and I will now go through the steps one by one. So for simplification, I will switch to 1D and go through the method using an example case in which the data is at 0.5 millimeter isotropic resolution, and the network is trained at 1 millimeter isotropic resolution. So when the image space and the case space of the input data are like this, downsampling in the image space can be represented as multiplying 2 different com functions that have different shifts. This is analogous to convolving com functions in the case space, which results in case space aliasing. And please note here that the high frequency information of the original data is not lost, different from the case where images are resized by cropping the case space. So because we sampled every other lines for the red and blue sampling cases, the resulting alias case space are different, and it is clear that the sum of the red and blue sampling cases is the original local field map, and therefore the sum of the 2 case spaces is the original case space of the local field map. So step 2 is network inference. The network conducts a dipole deconvolution at 1 millimeter isotropic resolution, which is a dipole division in case space. And network inference is done for each of the downsampled local field maps, generating different QSM maps. These maps are assembled by adding the maps together. And recalling that the sum of the case space of the downsampled local field maps was the original local field map, the case space of the assembled map is the case space of the local field map divided by the alias dipole kernel of 1 millimeter isotropic resolution. And of course, this would result in an erroneous map. So finally, we will look at the difference between the assembled erroneous QSM map and the desired QSM map. In the K-space, the desired QSM is local field map divided by the dipole kernel of 0.5 millimeter isotropic resolution. The assembled QSM map, on the other hand, is the local field map divided by the alias dipole kernel of 1 millimeter isotropic resolution. And therefore, we have to compensate for this difference by multiplying by the wrong kernel and dividing by the right kernel. Unfortunately, because the two kernels share the central part of the K-space, we only have to compensate for the edge of the K-space. Here, because the dipole kernel of 0.5 millimeter resolution contains zeros, the kernel is truncated using a similar method to truncated K-space division. And by this dipole compensation method, the desired QSM map can be reconstructed. For quantitative comparison with Cosmos results, we trained a QSMnet at 1.5 millimeter resolution and used this network to reconstruct two different resolutions of 1 millimeter isotropic resolution and 1 by 1 by 3 millimeter cubic. We qualitatively and quantitatively compared the results with the Cosmos results. Furthermore, we compared with two different scenarios to reconstruct 1 millimeter data using QSMnet 1.5 millimeter. In the first scenario, which is interpolation, we cropped the K-space to generate 1.5 isotropic data and input this data into the network. Different from the proposed method, this cropping of K-space results in the loss of high-frequency information, as will be shown on the results. The reconstructed QSM maps are then interpolated to the original resolution. The second scenario, naive input, we naively input the data into the network regardless of the resolution difference. So this is the results of reconstructing 1 millimeter isotropic data using QSMnet trained at 1.5 millimeter. In the zoomed-in images, we can notice that the interpolation scenario discards the high-frequency information and smooths out the small structures, whereas the proposed method successfully preserves the high-frequency information. The naive input scenario seems to preserve the structure. However, the contrast is changed compared to the Cosmos reference method. The quantitative metrics NRMSE, SSIM, PSNR, HFEN calculated with respect to the Cosmos reference method conforms to the qualitative results, displaying the best metrics in the proposed scenario. The reconstruction results for the anisotropic data are similar to that of the higher resolution isotropic data. Again, in the zoomed-in images, the small structures are well preserved in the proposed method, whereas the interpolation scenario failed to reconstruct the details. In case of anisotropic data, because the contrast is severely damaged, the small structures are also not visible in the naive input case. And similar to the 1 millimeter isotropic data inference, the quantitative metrics conform to the qualitative results, displaying the best metrics in the proposed scenario. So this figure is a representative reconstruction result of 0.6 millimeter isotropic resolution QSM data acquired at 7 Tesla, reconstructed using QSMnet Plus, which was trained at 1.0 millimeter isotropic resolution. We are quite fascinated by this result, considering that Cosmos quality reconstruction of 0.6 millimeter isotropic QSM data is a fairly challenging problem. And furthermore, using this method along with QSMnet, a network for reconstructing chi-separation maps, we could also generate high-resolution positive and negative susceptibility maps in which we can observe the detailed structures that was hard to notice in the chi-separation at 1 millimeter isotropic voxels. So the method may be applied to other networks that perform dipole deconvolution, similar to maybe QSMnet. However, limitations do exist to the extent of resolution that can be reconstructed. We believe that the resolution or the voxel size has to be larger than half times the original voxel size, or these sort of checked artifacts start to appear. So to conclude, the proposed method successfully reconstructed data at resolution different from that of the training data. And the performance of the method is limited to that of the network used. For example, in this case, the performance of QSMnet Plus, because, of course, the network was used for the reconstruction. And by this, I thank you for your attention, and I'm open to any questions. Thank you.
Thank you very much for your talk. Very impressive data. So do we have any questions, Olivier?
No, there's no questions in the chat.
Anyone could raise also their hand if they want to ask directly to the speaker.
Okay, so there's one question in the chat. How well do you think your pipeline would work with much smaller voxels?
Oh yeah, that's a good question. And this one is actually the example of much smaller voxels. So it's 0.25 by 0.25 by 1.5 millimeter cubic resolution. And I used the 1 millimeter isotropic QSMnet trained at 1 millimeter isotropic resolution. So it's 4 times smaller in the in-plane direction. And these kind of artifacts appear because as I have shown in some of the previous slides, we have to compensate for the dipole kernel difference, and the extent of the central part of the K-space that is same between the aliased dipole kernel and the exact dipole kernel, it depends on the resolution difference. So yeah, I believe that we will need some kind of more high resolution network for reconstruction of the higher resolution data.
Okay, thanks. So one more question from Christopher Rowley. Given the tools that are available, what resolution would you recommend someone acquire the data in order to obtain good results if they wanted to apply these methods without too much debugging?
Okay, so for QSMnet Plus, which is trained at 1.0 millimeter isotropic resolution, I would recommend at least 0.6 millimeter isotropic resolution or higher. So you can use anything like maybe 0.6 by 0.6 by 1.2 or anything like that, but nothing less than 0.5 millimeter in any direction.
Okay, thank you. I think those are all the questions.
Thank you very much.
Okay, thank you again. So we are going to go with the last speaker of the day.